Methodical. Look at this grammar rule. E produces E plus T. It correctly generates mathematical expressions, but watch what happens to a top-down parser. The parser tries to evaluate E, but the first thing it sees is another E. It dives down, substituting E for E plus T over and over, trapped in an endless cycle without ever consuming a single character of input. Because of this structural trap, an LL1 predictive parser simply cannot function. It requires a clear path forward, but this left recursive rule forces it to stall permanently. To move forward, we have to eliminate this left recursion entirely. We process the grammar mathematically, breaking the loop while preserving the exact language it generates. This diagram illustrates the abstract pattern of direct left recursion. We have a non-terminal, A, that calls itself immediately. What follows is the recursive sequence, alpha, shown here in cyan. On the right side of the pipe is the non-recursive base case, beta, in blue. To break the loop, compiler designers apply a master elimination formula. We force the grammar to loop on the right side instead of the left. The original rule transforms into two new rules. A produces beta followed by A prime, and A prime produces alpha followed by A prime or epsilon. By locking this specific structural formula into your memory, you can safely rewrite any direct left recursive production you encounter. Let's apply that formula directly to the classic expression problem. Here we map the original grammar onto the master formula. Our starting non-terminal, A, is E. The recursive part, alpha, is plus T, and the non-recursive base case, beta, is simply T. Now we execute the substitution. The base case moves up, creating the safe rule, E produces T followed by E prime. The recursive sequence moves down, creating E prime produces plus T followed by E prime, or epsilon. The new E prime non-terminal acts as memory. If we want to generate a string like T plus T plus T, E prime simply repeats the plus T sequence as many times as needed on the right side of the tree. This repetition requires an exit strategy. Epsilon must be included at the end of the E prime rule, giving the derivation a way to successfully terminate without causing a new type of infinite loop. Often, a single non-terminal will have multiple recursive and non-recursive options. This grammar shows S producing SA, SB, or C. Our recursive alphas are A and B. Our non-recursive beta is C. The generalized rule requires all non-recursive parts to connect to the new prime non-terminal. So S produces C followed by S prime. Then all the recursive sequences branch from S prime, resulting in AS prime, BS prime, or epsilon. This logic handles any number of productions. You simply group your alphas, group your betas, and let the formula organize them. Look closely at this two-rule grammar. A produces BA, and B produces AB or C. Because neither non-terminal immediately calls itself, this looks perfectly safe. But watch the expansion. If we expand A into BA, and then substitute B with its own rule, AB, our string becomes ABA. The grammar looped right back to A. To fix this, we have to force the recursion out into the open. We take the production for A and substitute it directly into the rule for B. B now produces BAB or C. Notice the result. B immediately calls B. We have successfully converted the hidden loop into standard, direct left recursion. Indirect left recursion is just direct recursion spread across multiple steps. Once you substitute your way down the chain to expose it, the problem is ready to be solved. Try applying the master formula to this newly exposed direct recursion. The formula is provided in the corner as your guide. Let's check the result. First, isolate the components. Our recursive alpha is the sequence AB, shown in cyan. Our non-recursive beta is C, shown in blue. Substitute those into the formula. B produces CB prime, and B prime produces ABB prime, or epsilon. The recursion is neutralized. This flowchart illustrates the universal procedure. Step 1. Check for indirect recursion. Step 2. Substitute to make it direct. Step 3. Apply the elimination formula. This breaks the structural loops that trap top-down parsers, while generating the exact same valid strings. With left recursion removed, the parser can safely move forward. But before we can actually build an LL1 predictive parser, we have to solve one final ambiguity, deciding what to do when multiple rules start with the exact same sequence. That requires left factoring.